Hello chemists, today we are going to be looking at 13C NMR spectroscopy, the third and final type of spectroscopy we are investigating in this topic. 13C NMR spectroscopy uses carbon-13, an isotope of carbon with an uneven number of protons and neutrons. This uneven number of protons and neutrons mean that when the carbon atom spins, as all atoms do, that spin is detectable because it is uneven. The number of protons and neutrons are uneven, so you can detect it. Think of it like a wheel with an off-center weight. You can, if it's perfectly balanced, you can't really tell when it's spinning by looking at it, but if it is unbalanced, it'll wobble. So basically, 13C NMR looks for that wobble. And you have some way of detecting that wobble, and you use a magnetic field to flip the spin of the atoms. And when that spin is flipped, you can detect that. When that spin is flipped, how much energy it takes to flip that spin depends on how many things the carbon is bonded to. So when you look at a 13C NMR graph, you will get peaks at different points based on the carbon environment of the atoms. What do I mean by carbon environment? Well, if we look at this molecule here, this is a 3-methyl-3-ethyl pentane. We've got an ethyl and a methyl all at the both at the 3 position on a pentane. So with 13C NMR, we are obviously looking at the carbons. There are 5, 6, 7, 8 carbons in this molecule. And we're basically looking at how they differ from each other. What are they bonded to? This carbon here is at the end. It's bonded to 3 hydrogens and a carbon, and is in the same situation as this carbon here, which is bonded to 3 hydrogens and a carbon. Ditto for these two. They are the same as each other. This one is bonded to 2 hydrogens and 2 carbons, and this one is also bonded to 2 hydrogens and 2 carbons. And once again, same thing here. This carbon is bonded to 4 other carbons. It is in the same situation as all the rest of them. But they're different from each other. So these 2 carbons are in the same environment, or have the same environment. These 2 have the same. This one is different from either of those pairs. And then we look at the ones on the side chains. It would be easy to look at this carbon here and this carbon here and say those are the same. They're both bonded to 3 hydrogens and a carbon. Unfortunately, they're not. Because the carbon here is at the end of an ethyl group, it's bonded to a carbon and 3 hydrogens, but that carbon is bonded to a single carbon, whereas this one down here is bonded to 3 hydrogens and a carbon, but that carbon is bonded to 3 other carbons. So basically, the fact that the carbons are in the same position, but the ones next to them are not, cause them to be different. It is asymmetrical. Basically, when you're looking at 13C NMR structures, you are looking at what are the things bonded to, and what are the things they're bonded to, and what are the things they're bonded to, et cetera, et cetera. And you're looking for ways in which those are different. So what we end up with is, on these side chains, we end up with a total of 1. So for the total molecule, we end up with a total of 1 carbon environment, 2 carbon environments, 3, 4, 5, 6 carbon environments in this 3-ethyl 3-methyl pentane. The graph we get ends up looking like this. This is not for 3-ethyl 3-methyl pentane. This is for a different molecule, but we end up with a graph that looks something like this. All you are doing in this graph is you are looking for how many peaks are there. In this graph, there are 1, 2, 3, 4, 5 peaks. That means I should expect to see 5 carbon environments, and in fact I do. I see this one here is different from this one here. Sorry, got to do my color coding. This one here, which is different from this one here, which is different from this one here, which is different from this one here. Even though the 2 on the end, this one and that one, are both CH3s. This one here is bonded to a carbon which is double bonded to an oxygen, and this one here is bonded to a carbon which is bonded to two hydrogens and another carbon. So basically, the things that are bonded to them make the difference. We ignore the oxygen right there. We don't have anything to do with it because it's not a carbon. We ignore the hydrogens because they are not carbons. All we're looking at here is carbons. You count the number of peaks, and that tells you how many carbon environments are present. This is useful for telling whether there are side chains in a molecule or whether the molecule is just really, really long. Because if you have a pentane, or sorry, if you have an alkane with a really, really big mass, you know it's either one single really, really long chain, or it's a shorter chain with some side chains. The IR and the mass won't tell you which one is which, but the NMR will. You can use it to finally put the two of those together, and that'll tell you the number of carbon environments, and you use that to work out what the molecule is. So a little bit more practice on this, and we will finally have enough information to go from just some graphs to the complete molecule.